Welcome to our comprehensive guide on the utilization of statistical methods for production monitoring. As industries strive for higher quality and efficiency, statistical tools have become indispensable in both development and manufacturing. From automotive to pharmaceuticals, the adoption of these methods has driven significant improvements. In this video, we'll explore why statistical methods are vital, how they support consistent product quality, and the collaborative efforts between industry and regulatory bodies to establish best practices. Let's begin by understanding the growing importance of statistics in modern production environments. The purpose of this technical report is to introduce relevant and easy-to-use statistical process control (SPC) methods tailored for the pharmaceutical and biopharmaceutical industries. While advanced statistical techniques like multivariate models and design of experiments (DOE) are excluded, we'll focus on practical tools that can be readily implemented. Additionally, we'll provide an overview of acceptance sampling, ensuring you have a well-rounded understanding of quality control strategies. This approach aims to empower professionals with actionable knowledge for real-world applications. Statistical methods are not just about numbers, they're about making better decisions. By providing objective evidence, these tools help manufacturers detect important signals and avoid overreacting to normal variations. It's crucial to first define the question you want to answer, then select the appropriate statistical method to guide your decision-making. Timely data analysis enables prompt detection of process deviations, supporting both process understanding and effective responses to variability. Remember, statistics are a means to an end: improved quality and informed choices. Before diving into the tools, it's essential to clarify some key terms. We'll discuss both specification and process control limits, process capability, and types of variability. Understanding these concepts will help you interpret charts and data correctly. Specification limits define the boundary between acceptable and unacceptable product, while process control limits indicate typical versus unusual process performance. Recognizing the difference between common cause and special cause variability is fundamental for effective process improvement. Specification limits are set by manufacturers based on therapeutic and regulatory requirements. They mark the threshold between acceptable and unacceptable quality. Exceeding these limits can result in loss of value, increased costs, or even safety risks. These limits are driven by the intended therapeutic effect and potential toxicological impacts, ensuring patient safety. It's important to remember that specification limits are not the same as process control limits. They serve different purposes in quality management. Process capability describes how well a process meets its specification limits. A high-capability process has low inherent variation, meaning most results are comfortably within the limits. Conversely, a low-capability process shows greater variation, with results more likely to exceed limits. Visualizing this with histograms helps identify whether your process is robust or needs improvement. Understanding process capability is key to maintaining consistent product quality. Statistical process control limits are calculated from historical data and define the typical operating range for a process. Unlike specification limits, which relate to product quality, control limits help detect when a process may be unstable or out of control. Prompt recognition of deviations from these limits enables timely review and process improvement. It's important to note that statistical significance doesn't always equate to practical significance. Context matters when interpreting results. Stable process is consistent and predictable, showing only common cause variation. In contrast, an unstable process exhibits special cause variation, making it unpredictable and inconsistent. Statistical tools help differentiate between these states, allowing for targeted interventions. Recognizing whether your process is in control or out of control is fundamental for effective quality management and continuous improvement. Warning or alert limits are typically used during development or process monitoring to detect trends and gain deeper understanding of process consistency. Exceeding these limits doesn't usually trigger formal investigations, but may prompt increased testing or proactive risk mitigation. For example, in microbiological monitoring, standard operating procedures can define specific follow-up actions. These limits are valuable for early detection and prevention of potential issues. Variability in production processes can be categorized as common cause or special cause. Common cause variability arises from typical fluctuations in materials, processes, or measurement systems. Special cause variability, on the other hand, results from unexpected events or circumstances. Distinguishing between these types is crucial for effective process control and targeted improvements. Statistical tools are designed to help identify and address both sources of variation. Trends refer to ongoing changes in the average or variability of process results. Analyzing trends helps detect patterns that could lead to future quality problems or signal upcoming changes in performance. Regulatory authorities increasingly require trend assessments during inspections, supporting corrective and preventive actions. Balancing the risks of missing potential hazards versus overreacting to minor changes is key when establishing monitoring practices. Even when all data points fall within control limits, certain patterns like erratic ups and downs or clusters may indicate underlying process issues. Small variations compared to control limits suggest a stable process, but sudden shifts or cycles can reveal hidden problems. Recognizing these subtleties is essential for proactive process management and continuous improvement. Sudden shifts in process level or cyclical patterns can indicate significant changes or time-dependent effects. Statistical rules such as the Western Electric or Nelson rules help detect these non-random conditions. Applying the right set of rules ensures consistent detection thresholds and supports timely review of potential events. However, using too many criteria can increase false positives, so it's important to tailor rules to your specific process. Statistical process control (SPC) tools are essential for monitoring manufacturing processes. Most involve plotting process data or calculated statistics on charts, with the vertical axis representing measured values and the horizontal axis showing time. Arranging data in time order is crucial for identifying patterns and trends. The main goal of process monitoring is to ensure statistical control, and various charts help assess this by adding numeric boundaries or limits. For conducting any statistical evaluation, certain prerequisites must be met. Data integrity and reliable measurement systems are essential. The attributes analyzed should be meaningful for the intended information, often focusing on critical process parameters or quality attributes. The level of effort and documentation should match the risk level. Additionally, results should maintain production order to reveal trends, and sampling methods must be well-defined to accurately reflect process characteristics. Grouping samples into rational subgroups maximizes the chance of detecting differences between groups while minimizing within-group variation. This approach supports meaningful comparisons, such as lot-to-lot or time-to-time analyses. Effective subgroup selection requires a solid understanding of the process and sources of variability. Proper subgrouping enhances the sensitivity of statistical tools and improves process monitoring accuracy. Using the right statistical tool depends on the process stage and data characteristics. For example, run charts are preferred for initial monitoring, while control charts are useful for ongoing production. Histograms help assess data distribution, and process capability indices compare process performance to specification limits. Understanding the strengths and limitations of each tool ensures effective application and reliable results. Uncharts are simple visual tools for monitoring data in sequence. By plotting measurements over time, they help identify general patterns and trends without assuming any specific data distribution. Run charts are often the first step in process monitoring and can later be converted into more advanced control charts as more data becomes available. Individual control charts or eye charts are used when single numeric measurements evaluate a quality attribute. They are most effective when paired with moving range charts to assess variability. Eye charts help monitor attributes with one measurement per lot, considering variability in process control assessments. However, variability may stem from multiple sources, so context is important. Moving range (MR) charts are used alongside eye charts to evaluate the variability of quality attributes. By plotting the range between successive data points, MR charts provide a coarse estimate of process variability. They are simple to create and help visualize general data patterns, but variability may include multiple sources, so interpretation should be cautious. Average and variability charts monitor the means of small data sets, leveraging the central limit theorem. These charts are effective for identifying patterns and assessing statistical control, even with non-normal data. Variability is plotted separately, and if it's out of control, the average chart may lose meaning. Sufficient within-batch samples enhance the reliability of these charts. Histograms graphically represent how often each value in a dataset occurs, helping to understand data distribution. They are valuable for analyzing both discrete and continuous data, summarizing large data sets and aiding in the selection of further statistical techniques. However, a single histogram doesn't show changes over time, so it's best used alongside other tools. Understanding the shape of a histogram is crucial. A normal distribution appears bell-shaped with most data near the mean. Bimodal distributions suggest two distinct populations, while skewed distributions indicate constraints or shifts in the process. Recognizing these patterns helps identify underlying issues and guides further analysis. Process capability indices such as CPK and PPK compare the specification range to the natural variability of the data. They answer the question, is the process capable of meeting its limits? These indices are useful for comparing processes and assessing relative risk, but should be used with other tools for a comprehensive evaluation. Remember, a single index doesn't capture changes over time. Value of a capability index provides insight into process performance. Low values indicate a high risk of producing nonconforming products, while higher values suggest the process is well within limits. It's important to assess whether the limits are relevant to the process and to consider risk-based reviews for ongoing control. Capability indices are best used for comparison, not for accepting or rejecting lots. WMA charts display the central tendency of data points, dampening individual variability to highlight underlying trends. This method is sensitive to small shifts in the mean, making it useful for detecting subtle changes. However, it may lag in response to large or sudden changes and is not designed to detect changes in variability. EWMA is especially helpful when measurement systems are noisy. Some charts track the cumulative sum of deviations from a target value, providing a quality control chart with memory. They are highly sensitive to changes in the mean, pinpointing when shifts occur. Some charts are valuable for early detection of trends, but there's a risk of overinterpreting statistical differences as product quality issues. Use them as part of a broader monitoring strategy. Efficient process monitoring often involves combining multiple statistical tools. For example, using X-bar charts, histograms, and Q-sum charts together provides a comprehensive view of process performance. This integrated approach allows for better detection of trends, shifts, and variability, supporting more informed decision-making and continuous improvement. Acceptance sampling involves taking representative samples from a lot to decide whether to accept or reject it based on quality levels. This method protects customers from defective products and is often used for incoming materials or when 100% inspection isn't feasible. Sampling plans balance the cost of testing with the risk of errors, supporting rational quality decision. There are various types of sampling: attribute and variable sampling, each suited to different data types. Single, double, and sequential sampling plans offer flexibility in balancing efficiency and risk. Acceptance sampling is not a guarantee of defect-free products but serves as an independent safeguard against catastrophic failures. It should complement, not replace, ongoing process monitoring and improvement.